Welcome to the Fractional Calculus Seminar. Today we have Professor Lehel Banjai, who is a professor at Mathematics Department at the Heriot-Watt University, which is a part of Maxwell Institute of Mathematical Sciences in Edinburgh, UK. Before coming to Edinburgh, he was at the Max Planck Institute of Mathematics and Sciences, Leipzig, and at University of Zurich. He obtained his DPhil in numerical analysis group at University of Oxford. He is best known for his work on numerical methods for time domain boundary integral equations and on convolution quadrature. In recent years, he has been active in researching numerical methods for fractional differential equations, time and space, a priori and posteriori analysis. His other interests include numerical wave propagation, data sparse methods such as H matrices and FMM, conformal mapping, etc. He was jointly founded and co-organized the One World Numerical Analysis Seminar, and he's currently acting as an associate editor of CINEM. We are very delighted to have you, Professor. Please begin your talk.
Thank you very much. Thank you very much for the kind invitation and introduction. And thank you for organizing this seminar. So I was looking at the list of talks, and it really shows what a rich and varied community it is. Yeah, so I'm very happy to give a talk in this series. Okay, so this is a talk about numerical methods for one particular problem, the fractional Helmholtz equation. So I'll give the structure of the talk is the usual. I will give the definition of the problem, the background, then move on to the numerical method, give some analysis of it, and conclude with numerical results. Okay, so to this audience, I maybe don't need to introduce the fractional Laplacian too much, but nevertheless, I'll go through the two main types of fractional Laplacians on the bounded domains, and then explain which one I will use in this talk. So if we don't have a boundary, if we are on the full space, there are a number of ways of defining equivalent waves of defining the fractional Laplacian. So we can use the spectral theorem, where if we project onto an eigenspace, then the action of the operator is to take the multiply by the fractional power of the eigenvalue. Then perhaps the most well-known is via the Fourier transform. So taking the Fourier transform, in the Fourier space, the action of the fractional Laplacian is this multiplier, so which fits also with both definitions continuously go to the standard definition of the Laplacian if you set s equal to 1. And then we can use the singular integral representation. Essentially, you can invert this Fourier transform definition. The PV here is the principal value integral, because as you see, this is a strong singularity here at x equal to y. So we have to take care of that. Okay, so all these definitions are equivalent. You can find books that prove this. And of course, there is also a probabilistic interpretation. So just like Brownian motion leads us to the famously to the heat equation, so a standard 2s stable Levy process leads us to the fractional Laplacian. Okay, or in other words, fractional Laplacian is the generator of such a process. Okay, so here I have a picture of such processes. So on the right, you have the usual Brownian motion, whereas on the left, you have a so-called Levy motion, where jumps can and do occur. I'll say a little bit more about that later. Okay, now on the bounded domain, things are trickier. So in this talk, I will simply consider homogeneous boundary conditions, though I will mention inhomogeneous conditions just on the next slide, I believe. And even with such a simple boundary condition, there are a number of reasonable definitions of the fractional Laplacian. So Okay, we can use some of the definitions on the previous slide and try and, in a sensible way, restrict the definition in this to this case. So we have then the spectral fractional Laplacian, where we again do the same thing. We take an orthonormal basis of eigenfunctions of say h10, and the action on the fractional Laplacian on the eigenfunction phi k is the multiplication by lambda k to the s, where lambda k is the corresponding eigenvalue. And then if you take a sufficiently smooth function in omega, you can expand it in these eigenfunctions and define the action on the fractional Laplacian component-wise. Yeah. Okay, and then you can extend it to by density to smoother to these h dot spaces which are defined here. With the negative exponent, this denotes the corresponding dual space, which can be identified actually with the sequences satisfying this kind of boundedness condition. Okay, so that's the operator that I will use here. Nevertheless, it's certainly not the only one, and maybe it's not even the most natural one. There is also the integral or Ries fractional Laplacian, and there we simply go back to this definition, the singular integral representation, and remember I want to do homogeneous Dirichlet condition. So what I do is I set u to be 0 outside of omega. Okay. I use the same definition of the fractional Laplacian. I simply assume that u is equal to 0 on the outside. This is the integral Laplacian. Now, both of them have a probabilistic interpretation. So let me explain it here, and then I'll explain it more on the next slide. So the integral definition, it's a generator of a so-called stopped Levy motion. How you can think about it is that you have the Levy motion, and once it jumps out of the domain, you kill the process. Yeah, and this is why you need a boundary condition everywhere outside of omega. Yeah. Whereas with the spectral one, you only need a boundary condition on the boundary of omega, because what you do is you take a standard Brownian motion, which will hit the boundary, and then you subordinate it. So you travel essentially along the Brownian motion with a Levy motion. This is a very hand-waving explanation. So what I like to do is then show this Feynman-Kac formula that in formulas explains this, what I just said in words. So here's the Feynman-Kac formula for the integral version. Yes, I begin with the integral version, and let's think about it first. So here you see I have a non-homogeneous boundary condition and also a forcing term. But let's, for the moment, just think of not having the f, or f being 0, and just having the g. Then then in this formula, we only have the first term. I don't know, do you see my mouse when I move it around?
Yes, we can see your mouse.
Okay, good. Okay, so yeah, so what this is saying is that the solution u is given as an expectation, where this x is a 2s stable Levy path. Yeah, the sigma omega is the time at which it exits omega. Yeah, so thinking of the previous picture, yeah, you think of this Levy path. At some point, it jumps out of omega. You take the value of g there. Yeah, and then you take the next path. Yeah, and take the average, and that gives you your expectation here. So you see that you need the Dirichlet data everywhere outside of omega. Okay, and then if you have an f, you pick up f along the way. This is this integral. Okay, so that's the integral version. And as I've been talking about it, this sounds like a possible numerical method. And indeed, there is a nice paper here that I cited, which does it in an efficient way, which extends the classical Wolfram sphere methods from the Brownian motion case to this case. Okay, So that's the integral version. For the spectral version, here it is. Let's think of the case again with f equal to 0 and just having a g. Now the g is only given on the boundary of omega. Okay, so again, we just have this first expectation. So I don't define everything here, but I'll explain it now. So what's happening is that you have just the Brownian motion, yeah, and at some time tau omega, it will hit the boundary of the domain, yeah, and then you subordinate this Brownian motion, you travel along it using the Levy motion, yeah, and you take the value of g at that point on the boundary, yeah, and then you again do you think of a kind of a Monte Carlo method. Okay, and then if you have an f, you pick up values of f along the way as well. Now, I remember when I first saw this, I was a little bit worried. Well, what does that mean? That means that I'm still picking up the value of g that I would have even if I had just the Brownian motion. Yeah, the subordination doesn't seem to make any difference. Yeah, and indeed, actually, one way of implementing non-homogeneous boundary conditions for the spectral version is to do a harmonic lifting of the boundary condition and then solve the spectral fractional Laplacian with a zero boundary condition and just a right-hand side. Okay, so these formulas are very pretty and they tell you a lot about the behavior of these Poisson fractional Poisson problems. And again, needless to say, this can be a basis of a numerical method. Okay, so that's my introduction. Yeah, so please interrupt me at any point. Of course, that's my very brief introduction to the definition of the fractional Laplacian that I'll use in this talk. There are many applications, and this area has been really increasing exponentially in recent years. So one of the flagship applications was in porous media, and I believe there is a planned talk in this series on porous media in a few weeks' time. Then maybe, well, the one that actually motivated this talk is this paper by Weiss, Vanders, and Antil from 2020, where they looked at some geophysical applications and using, well, also looking at experimental results, but also deriving an equation using a non-local constitutive law. They derived equation that will eventually simplify to what I want to look at today. And there are many other sources of motivation, and you will find them under the name of anomalous diffusion usually. And yes, so perhaps going from modeling ink in photocopiers to things like predator search patterns. So this is a famous paper where they were looking at the behavior of predators. So for example, a shark. Yeah, if there is a abundance of food, then it seems to search the space using a Brownian-like motion, whereas if there's a scarcity of food, then it seems to use some kind of Levy motion, where the data suggests that the power is 1/2. Okay, so there are many nice examples where this may be the correct model. Okay, so often it is purely phenomenological, that people look at the data and then fit a model to that, and less often, but also it is derived using some constitutive law. Okay, yeah, so now I think I can state in many ways a simple problem that I want to look at, but that will be a good vehicle for me to explain some techniques that I wanted to talk about, but also is useful in practice. So I'm looking at numerical methods for the fractional Helmholtz equation. Yeah, so if you put S equal to 1 here, this would be a standard Helmholtz equation, except that usually you would have k squared here. I assume that k is positive, i.e. k is a real number. In fact, everything goes through with k in the complex plane away from the branch cut along the negative real axis. Yeah. But for simplicity of some of the formulas and estimates, I remain with k positive. The fractional power s is between 0 and 1. And I'll say in a minute why we have a fractional power here as well. Okay, so I'm assuming the spectral fractional Laplacian. So remember this here, the zero boundary condition is encoded. Yeah, so really that's why I'm not writing a boundary condition here. It's sort of hidden in this operator. Okay. Okay. Now, is there a solution? Well, we do need to make a condition. Yeah, we need to assume that the k avoids all the eigenvalues of the Dirichlet Laplacian. Okay. And now here you see one motivation for raising the k to the power s as well. Simply then it's easier to write this condition. It's independent of s. Yeah, it's the same condition for all s. Okay. And then you can write down the solution as an expansion in the eigenfunctions. Simply you project your data f onto the basis of eigenfunctions, yeah, and then the action on that subspace is to multiply by the inverse of lambda j to the s minus k to the s. Okay. And under this condition, this is well defined, and you can it's well posed. You can put a bound on u in terms of f if f is in this h to the minus s space. So so that's the setting of the problem that I want to investigate numerically. Okay. So yeah, so motivation really comes from this paper on geophysical electromagnetics. And of course, it comes up in other situations as well. In particular, it comes up with a different sign here, with a plus. Yeah. For example, in this paper by Burrage from 2012, but also it comes up when you time discretize, well, equations fractional in time and space, or they can be fractional just in space, of course. And so, and here's another reason maybe to have a fractional power here as well, and that's that equations of this type are sometimes called the neutral fractional equations, and they, as far as I understand, they conserve some wave-like properties. Yeah, the solutions of when the power of which makes sense. I mean, where the power of the derivatives is of the same order in time and space. Okay, so that's the setting. So why talk about this? Is it trivial or not? Well, I think it's not. So the computational challenges are, of course, the non-locality. The fractional Laplacian is a non-local operator, hence this fractional Helmholtz equation will certainly have non-local effects as well. Then something that happens invariably with fractional differential equations is that you will have some problem with the boundary. So unless your right-hand side goes very smoothly to 0 on the boundary, you will have, in fact, singularities at the boundary. Okay, so in particular, the smaller the s, the stronger the singularity. So here, the boundary behavior of this problem is known, and this is, I mean, in general, like that. For example, the distance between that u behaves like the distance to the boundary to the power 2s. Okay. So if s is less than a half, this is already the derivative is unbounded. Okay, and here is a picture in 1D. And maybe I should have put a picture in higher dimension to see that it's, that it's, of course, along the whole boundary. It's not just a corner effect or anything like that. Okay, so we do need to deal with that. Now, as I said, this is, of course, and I just wanted to mention, of course, the same thing happens with if you have fractional in time. Yeah, you would have this singularity at the origin at time 0. Yeah, so it's very, in some sense, it's similar to that. Anyway, so how about numerical methods for this problem? Of course, there's a lot around there. Yeah, so I'll just mention a handful of methods, and there are nice overviews by now as well. So the methods also go along those definitions that we've given. So certainly there are, for k equal to 0, there is much more. So just for the fractional Laplacian, for the, say, fractional Poisson problem, there's a lot more out there. You can use directly the spectral definition in clever ways, as in these papers, using the spectral element method, for example. Then one very popular way, and which is what I'll end up doing today, is to approximate the action of this operator as a sum of these resolvents. Okay, so there are many ways of obtaining them. This is really just a rational approximation. And one popular way is to first derive an integral representation of this operator. So in this case, this so often goes under the name of Balakrishnan representation, and then apply some quadrature rule. Okay. And the advantage is that if this quadrature rule is very efficient, then you have only a few of these problems to solve, and each of them is a local problem and very well understood. Okay, so many people have done this in this setting. I'm citing Stenger because of his book on sinc quadrature methods, which we will come to. Bonito and Pashak made this particularly famous in this area. They looked at also more general operators than I'm showing here, so-called accretive operators. Then you can also use some data sparse methods to store these operators and use them efficiently, etc. Then another approach, which I will briefly talk about as well, is the extension to a degenerate local elliptic problem in a space that's one dimension higher. So this goes back in the probability literature to Molchanov and Ostrovsky in the 60s, made particularly famous recently by Caffarelli and Silvestre and Stinger and Torrea. And then for numerical methods, especially the group around Mehta had used it, but many others, including myself. What made it particularly attractive is that we can use all our knowledge of elliptic problems, both to prove theorems, but also to use numerical methods for a problem seemingly rather difficult. Okay, I'll come back to that. And of course, there are Monte Carlo simulations. Okay, for k different from 0, there's less around, but still there's plenty there. So here's a selection and you can separate the inverted commas easier case and more difficult case. So the easier case being with a plus here. Okay. There are again contour integral discretization methods. Here this is a paper we did on fractional wave equations, and then naturally these kind of problems occur at every time step. So we've looked at that. Now with the minus, there's less around. So of course, in this original paper, that I cited, that was the motivation for me to look at this equation. What they did is they multiplied both sides by the inverse of the fractional Laplacian. Yeah. And now they can but can apply this technique to discretize the action of the inverse of the fractional Laplacian, yeah, and obtain a large coupled but local system of equations. Okay, so this is possible and this works, but it's a little bit expensive because it becomes very coupled, all this stuff here. Okay. Then there was a very nice paper in follow-up from this paper. So in fact, Antil is in both papers and Weiss also, and Wanders as well. And Christian Glusser is one of the co-authors who I believe is speaking in this series as well in a couple of weeks. And there they use this extension approach, and I will mention this work a little bit later. In particular, what they do is in a nice way, they discover that you can you can approximate this problem with a series of such decoupled such problems where one of them is difficult, is of the type of the Helmholtz type, and the others are kind of with a good sign here. Okay, so that's the background. So let me now say what I propose to do, and the idea is extremely simple. So remember, for the spectral fractional Laplacian, we can talk about the eigenvalues. Yeah. So instead of writing here the minus Laplacian, let me just write a complex number lambda. Okay. In fact, because of my assumption on the Laplacian, let's think of lambda just being a real positive number, and the same as k. As I said, k could be complex, but let's for now leave it as k. Okay. And in fact, sorry, so here I do want to think of lambda as complex, of course. Yeah, so let's think of this function as a function of lambda in the complex plane. So, okay, so what do we have? We have a branch cut along the negative real axis. So we define this fractional power as the main branch, yeah, on the, yeah, and s is between 0 and 1. And we have a singularity at lambda equal to k. In fact, it's a simple pole. Okay, so what I do is simply remove and add back the pole at lambda equal to k. Okay, and this is the correct residuum. So this is what we take away, and this is what we add back in. So we obtain then two functions, f1 lambda and f2 lambda, where they have different behavior. So f2 lambda is a meromorphic function. It has this single simple pole at lambda equal to k. Otherwise, it's analytic. Whereas this function f1 of lambda has no longer, doesn't have a pole at lambda equal to k anymore. It's analytic there. It has a removable singularity there. But it has this branch cut along the negative real axis. Okay. And now you see what I did. I mean, it's okay. So I'm just stating this as it is. Yeah. So instead of doing directly this operator on the left hand side, I will do these operators on the right hand side separately, and indeed evaluating f2 at minus the Dirichlet Laplacian, I obtain a standard local Helmholtz problem to solve. Okay. And now all I have to deal with is this f1, which is an analytic function in the cut plane. Okay, and now you see the whole trick is to try and remove fractional powers of lambda and replace them with integer powers of lambda. Yeah, because integer power lambda is local. Okay. And then the typical thing is we write this function using the Cauchy integral formula. Okay, and here it is. Yeah, so we have now just the lambda with no fractional power at all. Yeah, this, of course, this function here, f, which I should have called f1. Yeah, oh, well, no, actually, that's just capital F1. Yeah, sorry. Okay, so let me do it this way. Yeah, so this gives us a formula where lambda appears just in an integer way. And now if we do some clever quadrature here, we've obtained exactly what we want. Okay, and hopefully we have these quadrature nodes in a nice place. Yeah, so that these problems are easy to solve. Okay, so the question is now how to solve this, how to choose this contour, and then how to perform the quadrature. Okay, so let's press on. And yes, and indeed, I mean, this sum here, it's a sum of rational functions. So really what you're doing is you're computing a rational approximation. So this F1 seems to have remained on my screen, so let me delete it. Okay. Okay, and then there are two ways of looking at it. So, okay, so we still need to discrete, if we want a fully discrete method, we still need to discretize in omega, yeah? And one thing you could do is you could first discretize in omega, so discretize the Laplacian, standard Dirichlet Laplacian, and let's say we're doing some finite element method, so A is the usual stiffness matrix, B is the mass matrix, yeah? Then what you need to do, you end up in the realm of matrix function theory. Yeah. So what you need to compute is F1 of this matrix. Okay. And of course, there is a lot of literature on that. Yeah. And there are very good methods there. So in particular, we will look at this paper of the three Nicks, Nick Hale, Nick Hyam, and Nick Trefetten. But one thing I want to highlight there is that there is one thing that one needs to be careful about, that a lot of these methods make use of the fact that the spectrum is finite. Yeah, it's the discretization of the operator. Yeah, and in order to create efficient methods. However, one has to be careful how one discretizes this Laplacian, because the correct space for discretizing, the standard Poisson problem might not be the correct space for discretizing the fractional Laplacian. Yeah, the standard Poisson problem will not have the singularity on the boundary. Yeah, and if you don't include that in the space, you'll be inaccurate. Yeah, so this is something to be aware of. Okay, then the other approach, which is in fact the approach I will take on in the next slide, is to do the discretization in omega afterwards. First, choose the contour. Now the contour has to avoid, the whole real line, yeah, because you don't know where the eigenvalues are, and there's no limit to them, yeah. Okay, now I just realized something, but it's okay. And then discretize the integral. Okay. There are many ways of coming to this, but there is one concern here, and that because you will eventually discretize omega in omega, that perhaps you're potentially using suboptimal choice of the contour. Okay. So anyway, let's look at the suboptimal choice of contour, perhaps suboptimal. Yeah. So let's remember we can represent this function just using the Cauchy integral formula. Yeah. So I choose this contour to go around the lambda where I'm evaluating F1. The K is no longer a singularity, so it's perfectly okay for this contour to contain K. I can increase it to contain K. However, we should be careful around the branch cut along the negative real axis. Okay. So now in the usual thing, that we did in our undergraduate studies in complex analysis, I increase this contour into this familiar Pac-Man figure. So now it contains K, but that's fine. It's not a pole. And it goes around the origin and it's kind of sort of enclosing the negative real axis. And then I make this outer boundary go to infinity. The decay is sufficient that the integral along it goes to 0, so that's fine. And I let this mouth of the Pac-Man close in on the negative real axis, yeah, so that what we end up with is just an integral around this negative real axis. And when you rearrange things, you obtain a real integral. Yeah, the imaginary parts cancel, and this is what it looks like. Yeah, so it's an integral from 0 to infinity, where in this picture you're thinking that 0 is here and infinity is here to the left. Okay, this should not be k squared. This should be k. Sorry about that. And yeah, and this is the formula that we obtain. It only contains a lambda here, so no fractional power of lambda. And now if we can construct some clever quadrature here, we are done. Okay. Now, I'm surprised that I haven't seen this formula elsewhere, except already in 1960, a paper by Kato. There is almost identically looking formula, but with a plus here, which is the representation of this fractional Helmholtz equation, but with a plus here. Yeah, the sort of easier, what I call the easier case. Yeah, so that's certainly there in the literature. And here it is for this case. Okay, and now, ask any numerical analyst, they will have a good idea of how to do this efficiently. And here is one option, which is quite popular, and that's to transform things in order to use sinc quadrature. So there's a nice overview of in 2014 of Trefethen and Weidemann on trapezoidal quadratures, which I think can be understood as that. So what we do here is we do a change of variables. We push out the singularity at 0 to minus infinity, and we here we already have the integral to infinity, but the decay is quite slow. You see the decay in R is R to the -1 minus S. So we push that faster to the infinity as well with this exponential change of variables. And now what we end up with an integral along the real axis from minus infinity to infinity, where the integrand is analytic around along it. In fact, it is analytic in a strip of width 2 pi. From minus pi to pi. Okay, and this is the perfect setting to apply sinc quadrature and to obtain error estimates for this sinc quadrature. So what does the sinc quadrature do? Well, simply what it does, it puts a uniform mesh on this real line and applies the trapezoidal rule there. So just evaluates this function, and at each of those equally spaced points, of course, you multiply it by the step and you sum it up. Okay. And okay, so this is I'm already doing it for the full operator, not just for this F1. So I need this Helmholtz part, have this infinite sum, and the error is exponentially small in the sense that the error is e to the minus 1 over h, where h is this step in the quadrature. Okay, so very fast convergence. Okay, now, of course, that's not enough. It's still not a practical quadrature because we need to truncate this sum with these things are decaying to infinity. So eventually we can truncate them at some k plus and k minus. There's a slightly different behavior in the positive and negative part here. And you can see then to still have an error of order e to the minus 1 over h, you need to choose the number of elements of this sum to be proportional to 1 over h squared. In other words, there's convergence of e to the minus square root of k, where k is the number of terms here. Okay, there are other approaches. You can use the so-called double exponential transformation and other things, but this is good enough for now. Okay, so lots of things there, but let me summarize the relatively simple now situation that we are in. Okay, so I need to be careful with time. I'm being very slow. So to solve this fractional Helmholtz equation, we approximate the U as a sum of solutions of a series of local problems. The U tilde is a solution of a Helmholtz problem, okay? And these ULs are solutions of reaction diffusion problems, where you see we have a plus here, okay? So these are this is a good shift, This is a positive operator, this is a positive shift, okay? But we have some constants in front of it. These are these quadrature nodes, I guess, okay. Okay, and somewhat different behavior when y is greater than 0 and less than 0, but it's all quite harmless, except that it's not completely harmless. So you see this in particular, let's highlight this, the coefficient multiplying the Laplacian can be tiny, and not only that it can be tiny, it has really ranges from 1 up to 10 to the minus whatever. A very small number. So this creates numerical difficulties. But anyway, let me show you the pictures. So remember, we split the solution into 2 bits. One is the local one. This is the second one. And here's the solution to that local one. That's, you see the oscillations coming from the fractional Laplacian. And then we have this non-local one. That actually looks easier, except at the boundary where you see you have this kind of nasty boundary behavior. Okay, Okay. Let's look at now these singularly perturbed problems. Yeah, so remember, we do need to look at how are we solving problems like this, local, but with a coefficient here that can be small and can be 1 as well. Okay. Now it's well known that what appears in these cases is that you have boundary layer behavior. Okay, so there's quick transition away from the boundary. You can split the solution into bits, one smooth and with controlled derivatives, and one which is a boundary layer term, which you see decays exponentially away from the boundary. So your mesh, if you want to be accurate, usually needs to capture this behavior near the boundary, and that's everywhere on the boundary. Yeah, you still have, of course, corner behavior. Okay, so and that reminds me that what I didn't say is that while what I've said up to now, holds in any dimension and any kind of domain. Now I'm looking at some details on in 2D on polygons. Okay, and I want to apply a numerical method there. That's appropriate. Okay, so what I will use here is an hp-finite element method. So this is from a work with Markus Mellenk and Christoph Schwab, and goes back to their much earlier works. So what we do is we split the polygon into patches, and then in each of the patches that touch the boundary, we do a particular type of refinement towards the boundary. So here, this is the boundary. Yeah. So if you have a patch like this, we have L levels of geometric refinement towards it. If you have a corner, that's slightly different, but still you have L levels of refinement towards that. Yeah. And then you have these mixed elements that have both behaviors. Okay. And away from the boundary, we use just high order finite elements. Well, we will use high orders here as well. Okay. Okay, here are some details, but the main thing I summarize the results here is that we can obtain, if we choose L levels of refinement, if you choose a if you choose a P order finite element method, and we use P refinements towards the boundary and the corners, we obtain an exponentially small error in P in the energy norm. And yes, I didn't put the size of the system, but I believe it scales like P to the 4, if I remember correctly. Now, but there's one crucial thing is that you see, I mean, these are very unbalanced meshes. Yeah, you have these long, thin elements near the boundary. Yeah, and this will do, mess your spectrum rather a lot. Yeah, and you can estimate your spectrum using well, inverse inequalities. Yeah, finite element inverse inequalities, and indeed, you see that that the eigenvalues of your discretization of the Laplacian, in fact, grow exponentially in P. Okay. Okay. So that'll have importance for the next thing. Okay. So this is again some summary of what I did so far. Yeah. So we need to solve one Helmholtz equation and order capital K. Singularly perturbed problems with the accuracy being e to the minus alpha square root of k. The hp-FEM in omega introduces another e to the minus p error. So if we choose k equal to p squared, local singularly perturbed problems to solve, then we obtain overall this error. Okay, so I'm hiding lots of details, but that's the behavior. But there are these, so you see, I mean, these boundary layers, what I want to highlight here are not artificial. It's not that I did a bad discretization along the way and this created these problems that required the discretization of the capturing of the boundary layer. But really these boundary layers are there to trying to resolve the boundary singularity that's inherent in these fractional problems. So that's really there. unless F has a strong compatibility, boundary compatibility. Okay, so let's look at now this other approach where we first discretize in space in omega, then estimate the spectrum, yeah, and then use this knowledge of the spectrum to deform the contour in an optimal way. This is done in this paper using conformal mappings, and what can be obtained there, a seemingly really much better result, yeah, that the error of this quadrature now is not e to the minus square root of k, but it's e to the minus k, okay? However, and we do have a division by the logarithm of the ratio of these bounds on the eigenvalues, okay? So this logarithm looks innocuous, however, and indeed it is, yeah? So if you do a standard h-finite element mesh for you know the Laplacian, the integer Laplacian, this logarithm of this ratio would indeed be just logarithm of 1 over h, and you would not really worry about that term much. Yeah. Now, in this kind of somewhat extreme HP case, but which does make sense in our setting, the logarithm of m over m is actually proportional to the polynomial degree p. And then you see, if I choose this capital K as, so that means that to obtain here an error of e to the minus p, I again have to choose capital K as p squared. So yeah, so if, that's my point. So if you do take into account, yeah, that you do need to choose this specific type of mesh in this setting, then you end up having the same kind of behavior, yeah. So with that in mind, this is an excellent approach. And as it, this is just a picture of half of the contour, and it also goes along the branch cut, but does this thing into the complex plane as well, which is not so nice that we have to do that, but it still gives good results. You know, if I can, I would maybe prefer to remain, you know, real, so to say. Okay, so I know that. Well, okay, I mean, let me, because I do, I guess, have a bit more time, but let me briefly go through another approach, yeah? So there is this extension approach, yeah? And the idea there, which is nicely described in one of Aldinotti's work, is that yeah, so yeah, you have your Levy motion on say on your table, yeah, and it can jump, yeah. But another way to think about it is that you let a, you know, that you let a Brownian motion, you know, go around your room, and you only record it when it touches your table, yeah. This is what allows for jumps, yeah. And indeed, in this way, you can model, well, you can understand the fractional Laplacian on the RD as a local elliptic problem on an extended domain. Yeah, I mean, what's well known is the case 1/2. Yeah, and also it's well known, I mean, in the community of people doing boundary integral equations. Yeah, so the community doing boundary integrals is really doing the opposite. Yeah, so if you say you want to solve an elliptic problem on a domain, you instead solve the non-local boundary integral equation on a manifold of one dimension less. Yeah, here you're kind of doing it going in the opposite direction. Okay, and this is then the setting. So this is now an elliptic problem with a weight here y to the alpha in the diffusion. It's defined on a cylinder in the extended domain. So yeah, you have your omega, and then you extend it into a infinite cylinder. Yeah, in RD plus 1. On the lateral boundary, you put zero boundary condition, and if I take the Dirichlet condition on omega to be little u, then the normal derivative of the solution of the extended elliptic problem gives me the fractional Laplacian applied to U. Yeah. In other words, the action of the fractional Laplacian is the Dirichlet to Neumann map of this elliptic problem. Okay. And now the attraction of this also is that it's very easy to extend it to more complicated problems. So you see now this perturbation on omega, which minus k to the SU, simply becomes a modification of the boundary condition on omega. Okay. And now we can, and this was in fact done in this paper as well. Okay. And now there's a lot of machinery behind and a lot is known about these problems. So for example, you can expand the solution into eigenfunctions again in both omega and in the extended domain. And in the extended domain, these functions, they have a known behavior. They have a singularity close to U of type y to the fractional power, and they're analytic in this extra direction, and have an exponential decay there. Yeah, and now we are very much again in the situation that we had with our singularly perturbed problems. Again, we have this kind of exponential decay away from zero, and some fractional power at the boundary. So you can think of that this behavior is very similar to the behavior at the corners of the singularly perturbed problems that we looked at. And then again, many things you could do. And one thing I will do here is to do again this kind of geometric scaling. So if you think of here along the y-axis is your omega, yeah, this is the extended direction, yeah. Then we have a geometrical subdivision of this interval. Of course, we cut somewhere because we have an exponential decay, and we do polynomial approximation there. Okay, so I know that this is going a little bit fast, but let me then come to the which is the nice point, come to the fully discrete system here. So what you obtain, because you see you have a tensor product domain omega times this extra dimension, you do a finite element method in each. So what you obtain is a tensor product linear system. So here again, the A's denote stiffness matrices, B's the mass matrices, and the subscript denotes, where this lives. So omega in omega, the y in this one-dimensional extended direction. Yeah. And you see, this is this perturbation due to the Helmholtz equation. Okay. And this E1 is, you can think of it a restriction onto omega. Okay. So what the linear system looks like, so all these matrices are symmetric and positive definite. In particular, the AYs and BYs are also small because it's just a 1D problem and we do a very efficient method. And we have a rank 1 perturbation, okay? And now if we solve the generalized eigenvalue problem related to just this operator here on Y, we can diagonalize the system and obtain again a decoupled set of discretized reaction diffusion problems. So a very complicated roundabout way to arrive at in a discrete way something similar. Okay. There are many advantages to this approach because we can understand the whole thing as a fully Galerkin method, but algebraically at the end it looks very similar. Okay. We have analyzed the behavior of these coefficients here, which are the eigenvalues of that generalized problem. Again, very similar to the estimates that are given before. They contain a very large range. And then what was noticed very nicely in this paper is that, of course, you have a rank 1 perturbation, and then Weyer's theorem tells you that the eigenvalues will be interlaced from this case k equal to 0. So what will happen is that all the eigenvalues will be positive except for 1, yeah, which will be around minus k. Okay, so a very similar thing. Okay, so let me now very quickly conclude with some numerical methods. So I will look at the problem with f identically equal to 1, so the right-hand side, so it doesn't go smoothly to 0. As remember, the solution splits into 2. Okay, so okay, sorry. Oof, okay. And here's the convergence order. So what I'm looking at the convergence of the 3 methods that I've discussed. One, the sinc quadrature, one, the extension, and one, the conformal mapping approach. For if I look at the error against the polynomial order, we see nice exponential convergence. When you look at the error compared to the square root of the number of linear systems that we need to solve, we see exponential convergence. However, sinc doesn't perform as well as the extension and the conformal mapping approach. Then for a small s, which is always much more difficult, similar behavior is seen, but the difference is larger, though this time the extension problem doesn't behave as well. Okay. But still, we see nice exponential convergence with all. And now to conclude, let me look at something that goes a little bit beyond this basic theory that I've shown. Let's look at just a picture of the checkerboard example. So k is equal to 16 here, and the A jumps. Yeah. So the domain, the square is split into a checkerboard, so 4 squares. Yeah. And in 2, the coefficient is what? Is equal to a quarter, and in the other 2, it's 4. Okay. And just to show the robustness of the method, and I'm not solving what I've written here, but I'm really solving the Helmholtz equation. Yeah. So there should be a minus ku. Okay. And okay, here is the picture of the solution, and you nicely see where I guess the diffusion coefficient is large here and small here. Yeah, so you have more oscillations here, and this is it in a 3D plot. This was all implemented in NetGen ngSolve. All is there, so the implementation is easy. Okay. Okay, so then to conclude, I introduced a simple Dunford-Taylor representation for the fractional Helmholtz equation. The crucial thing I wanted to highlight is that you can do either way, discretize, first the contour, then the Laplacian, or either way, but you need to be careful that you use the correct space in omega. And there's a lot more that could be done. And if you really care to solve this problem very efficiently, there are many tricks that you could apply. Yeah. And yeah, that's all I wanted to talk about today. So thank you, and sorry for taking up almost a full hour.
Thank you very much for the nice talk. For the questions, please raise your hands. I'll call out your name in the order they appear on my screen. I see Professor Scalas has a question. Please go ahead.
Yes. So can you hear me?
Yes, I can hear you, Enrico.
Hi, Lehel, how are you?
Good.
Thank you very much. So thank you very much for your very interesting and clear presentation. So I have a question and a sort of question remark, let's say. So the question is related to your slide 17. If I remember correctly, so you can essentially use the problem. Well, this is also the remark, let's say. So the function that I see there seems incredibly similar, except for the minus sign at the denominator, to what you would get for say the function whose Laplace transform is a Mehta-Gleffler function somehow. So related to this is related to the what is called the Caputo derivative somehow. Maybe because you're decomposing, there might be this singular part behaving like that. But of course, there is a plus sign. So that one is for sure a probability density, the Lamperti probability density. But this one, I don't know. So.
Yeah. No, it's a good point, and there must be connections, because I mean this procedure that I'm doing, this looks very much like, you know, Henrich's real inverse Laplace transform. Yeah.
Exactly. Yes.
Yeah,
yes.
exactly. Yeah. So yeah. And yes, and this with the sign, exactly. I mean, this is what Kato was doing with the plus here. Yeah.
Yes. And then of course here you have some
and then it can be a
R plus lambda, which seems the Laplace transform of the exponential, which you don't have in the Caputo case. However, I mean, this is just I don't know. Yeah, I have to think about it. So in fact, many ideas came to my mind, but there is also the transparency in where you were showing somehow the relationship of the problem you were discussing. So you start essentially with the eigenfunctions of the Laplacian, and you mean the eigenfunctions in the domain you're interested in. Yeah. Okay. That was my question, because you were not mentioning domains there, but
yeah. Sorry. It's an omega. Yeah.
Yes. So and essentially, heuristically, you can use those eigenfunctions to expand your solutions, etc. But if you do this numerically, it's very slow.
Yeah. So
okay.
Yes, I mean there would be ways of maybe speeding it up or doing something clever, but yes, in principle, of course, unless your right hand side is very smooth, the decay of its coefficients in this expansion is very slow.
Okay, so it is not a viable way of computing the solution because of, so it's a form, I mean, you have the solution like that, but you cannot use it essentially for numerical calculation.
I wouldn't say you cannot. Yeah, perhaps, you know, I mean, I think there are methods that would do a spectrally accurate approximation of the Laplacian and then use that directly but in general, yes, I mean, the decay would be slow. Yeah.
And related to this, the numerical methods you present are faster than a Monte Carlo simulation?
Okay, so good question. So, I mean, okay, of course, they are very accurate, right? Which might be difficult to obtain using Monte Carlo. That's one thing. The other thing is, and this I'd love to hear, is that, of course, I can imagine if I have a plus, right? I can imagine a Monte Carlo method for that, because as you said, it's a probability density. But if I have a minus, then it's more difficult, isn't it? Right? Because it's not going to be an average of something.
Yes. So you have probably to use some tricks and like in quantum physics that you take some wave function and you square it, and then, so I don't know. Yes, that's right. You're right.
Exactly that point that you made now. Yeah. That's a possibility, but that's already.
Thank you very much.
Yeah. No, thank you.
Are there more questions? Okay, I don't see any more raised hands, so I just have one or two very trivial questions. So on slide 15.
I didn't hear the number. Sorry, can you repeat it?
On slide 15. Go on a little bit. Yeah, so I'm not quite sure how we Okay. How did you get this F1 lambda? Okay, F1 lambda is the term, and then you're writing it as an integral.
Okay, so yeah, so here you see, I mean, think of, okay.
Okay, this is just adding 0 on the right hand side to get.
Yeah, here I'm just adding and subtracting, but
Yeah.
but the reason, you know, the reason that I'm getting this coefficient is simply if you multiply this expression by lambda minus k and you let lambda go to k, you would get this coefficient, which shows that indeed lambda is a simple pole. Yeah. So basically this function behaves like this for lambda close to k.
Mm.
Okay, and then so that's fine. Yeah, and so what I've done here, I have taken away the singularity at lambda equal to k. So if you take this black, if you can, so if you are able to evaluate F1 at lambda equal to k. Yeah, it looks like it has a singularity, but it's a removable singularity. So F1 is analytic around k. And then I can write F1 just using the Cauchy integral formula. Yeah, so F1 of lambda is using the usual Cauchy integral formula around a contour, you know, encircling the lambda.
I see.
Yeah, because this is an analytic function here, and because I've removed k, I can even increase this to include k. Okay.
I see. I see the other trivial question I had, like in your slide 23, where you have this HP scheme. HP finite element. So what is the polynomial are you using for the construction of this HP scheme?
So we go up to whatever's allowed in the NetGen, and luckily NetGen can do it quite a high order. We seem to be only going up to order 6, but I'm sure I've gone further. I think
I see.
I think it can go up to order 12 NetGen. Maybe I'm not, but around there. Yeah.
Okay. I'll look at the documentation of NetGAN. I'm not acquainted with NetGAN, but my curiosity was like, what class of polynomials is it? Like Jacobi class of polynomials or the usual finite element polynomials?
It's the usual finite element polynomial. Nothing fancy there. The only fancy thing is this geometric refinement towards the boundaries. Yeah.
I see.
And this is more or less exactly like this implemented in NetGen and GSolve. I mean,
okay.
Yeah.
Okay. I think I get the high level idea of this. All right. So do we have more questions or comments? You can unmute your mic. Okay, I don't see any questions or questions anymore. So this is a good point to close this talk here. Thank you very much, Professor, for the nice lecture.
Thank you very much. Yeah, thank you for the invitation and the nice questions. Yeah.
My pleasure.